It is 1666. A young man sits in a garden in Woolsthorpe, watching an apple fall. His name is Isaac Newton. And in that moment, a thought strikes him like lightning. What if the force that pulls fruit to earth is the same force that holds the moon in its orbit? What if the universe doesn't need God's constant intervention? What if we could read the mind of the Creator by decoding the mathematics written into creation itself? Tonight we unravel the life of Isaac Newton, the man who turned the heavens into clockwork. He is perhaps the most paradoxical genius in history. To some, he is the cold rationalist who banished magic from the cosmos. To others, he is the obsessive mystic who spent more time on alchemy and biblical prophecy than on physics. In this episode, we'll trace his journey from a fatherless farm boy to the man who explained gravity. We'll see how he weaponized mathematics against his rivals, why he had a nervous breakdown that nearly destroyed him, and how his quest to decode God's design accidentally created the modern scientific world. Before we begin, a small invitation. If these quiet journeys help you slow your thoughts and ease into rest, tap like and subscribe so you can return whenever you need a gentle ending to the day. And if you feel like it, leave a comment below telling us where you're listening from. We love imagining these stories travelling across the world. So settle in and prepare to walk through the mind of a man who saw further than anyone before him. Not because he was taller, but because he stood on the shoulders of giants and then crushed them beneath his feet. This is the untold story of Isaac Newton. Chapter 1. The Making of a Chosen Man. To understand Isaac Newton, you need to start with a fact that shaped his entire psychology. He was born on Christmas Day, 1642, and his entire life he believed this meant something, that he was chosen, marked by providence for greatness. The birth itself tells you everything. December 25th, 1642, or January 4th, 1643, by our modern calendar. In a small manor house in Woolsthorpe, Lincolnshire, England, a premature infant was born to a 20-year-old widow. The baby's father, Isaac Newton Sr., had died 3 months before birth, leaving Hannah Ayscough alone, pregnant and terrified. And the baby was so small they said he'd fit in a quart pot. Nobody expected him to survive the night. Now here's what's important about that date. 1642 was the same year Galileo Galilei died in Italy. So as the old master of astronomy died, the new one was being born. Newton himself would later see this as cosmic significance, that he was meant to complete Galileo's work, to finish what the Italian had started. The fact that Newton survived at all was remarkable. Premature babies in 1642 almost never made it. He was so small, so weak that the women who attended the birth didn't think he'd live through the night. But he did. And that survival, that defiance of death at birth, would shape his personality forever. He believed he was meant to live, that God had saved him for a purpose. And this created a problem, because Isaac Newton never knew his father. His father was a yeoman farmer of modest means, who left a small estate to an infant son he would never meet. No male role model, no paternal guidance, no father to teach him or discipline him or show him how to be a man. This absence created a hole in Newton's identity, a void he spent his entire life trying to fill. He never felt he belonged anywhere. He never felt he owed anything to anyone. He spent his life trying to prove his worth to the world. Throughout his life, Newton would return to this birth narrative. He was born on Christmas like Christ. He survived against impossible odds like a miracle. He came into the world as Galileo left it, like a torch being passed. And his father's death before his birth meant he owed nothing to any man. These weren't just biographical facts to Newton. They were proof of his special destiny, proof that he was chosen, proof that the rules didn't apply to him. And then, when Isaac was 3 years old, his mother did something that Newton would never forgive her for. She abandoned him. Here's what happened. In 1645, when Isaac was 3, Hannah Ayscough remarried. Her new husband was Reverend Barnabas Smithy, a wealthy rector. Smith was 63 years old. Hannah was 23. And here's the crucial detail. The marriage contract stipulated that young Isaac would stay behind at Woolsthorpe. His grandmother, Marjorie Ayscough, would raise him. Hannah moved to Smith's rectory in the nearby village of North Witham, less than 2 miles away, but it might as well have been a different world. Think about this from 3-year-old Isaac's perspective. His father died before he was born, so he never had a father. Then his mother, the only parent he'd ever known, remarried and left him with his grandmother for a richer, older man. And over the next 8 years, she had 3 more children with Smith, half-siblings that Isaac barely knew. His mother chose a new family over him. The evidence of this trauma is undeniable. Years later, when Newton was 19 years old, he compiled a list of sins he was confessing to God, and one of the sins he listed was threatening my father and mother Smith to burn them and the house over them. This wasn't a metaphor. This was rage, fantasies of violence and burning. The depth of his abandonment wound laid bare in his own handwriting. And this abandonment shaped everything about Newton's personality. He had extreme difficulty trusting people, kept everyone at arm's distance, never married, possibly never had any romantic relationship at all. He formed very few close friendships, and when he did trust someone, like the Swiss mathematician Fatio de Duillier years later, he became obsessively attached, almost pathologically dependent. He perceived any criticism as betrayal. His scientific feuds were never just intellectual, they were deeply personal, because to Newton, any challenge to his work was the abandonment repeating itself, people trying to take from him what was rightfully his. Newton spent his entire life trying to prove he didn't need anyone. He worked alone, published reluctantly, shared nothing until forced to, and when rivals challenged him, he destroyed them utterly. Because to Newton, any challenge wasn't just academic disagreement. It was the abandonment repeating itself, people trying to take from him what was rightfully his. From age 3 to 10, Isaac Newton grew up with his grandmother at Woolsthorpe, and everyone who knew him agreed on one thing. He was a strange, angry, solitary child. The pattern was clear from the beginning. He was withdrawn, didn't play with other children, built models and mechanical devices obsessively, water wheels, sundials, wooden clocks. He drew on walls and furniture in his grandmother's house, spent hours alone. Neighbours thought him odd. Other children feared him or avoided him entirely. Even as a child, Newton's hands were always building. He constructed a working model of a windmill powered by a mouse running on a wheel. He built elaborate sundials that could tell time with remarkable accuracy. He made water clocks and flying kites with lanterns attached at night. These weren't normal toys. These were engineering projects, and the obsessive focus was already there. He would work on a device for days without stopping, forgot to eat when he was focused. His grandmother had to physically force him to take breaks. This pattern would continue his entire life, working to the point of physical collapse, complete disregard for his own health. Then in 1653, everything changed again. When Isaac was 10 years old, his stepfather, Reverend Smith, died, and Hannah returned to Woolsthorpe with her 3 younger children. Now, Isaac had to share his home with the half-siblings his mother had chosen over him. You can imagine the resentment. And Hannah had a plan for Isaac's future. He would become a farmer like his father, manage the Woolsthorpe estate, marry a local girl from the village, produce heirs, live the life of a yeoman farmer. This was a reasonable plan for a fatherless boy in 17th century England. But it was completely wrong for Isaac Newton, and what happened next would determine everything. Chapter 2. Failure at Ordinary Life. In 1655, when Isaac was 12 years old, his mother pulled him out of school and tried to make him a farmer, and it was a complete disaster. Here's the setup. Isaac had been attending the free grammar school in Grantham, a nearby town, boarding with a local apothecary named William Clark. But Hannah decided education was a waste of time for a future farmer, so she brought him home to Woolsthorpe to learn estate management. She expected him to tend sheep, manage crops, go to markets, sell produce. This would be Isaac's future. Isaac Newton was the worst farmer in Lincolnshire. He would be sent to tend the sheep, and they'd find him hours later, under a tree, reading a book while the sheep wandered into neighbours' fields. He was supposed to go to market in Grantham to sell produce and buy supplies. Instead, he'd go straight to his old room at the apothecary's house and read, forgetting entirely why he'd come to town. The specific incidents are almost comical. Sent to watch sheep, he built water wheels instead. Supposed to fix fences, he drew mathematical diagrams in the dirt. Asked to plough a field, he sat under a hedge reading. Neighbours complained constantly. Animals escaped. Crops were neglected. Hannah grew increasingly frustrated. This wasn't defiance. This was someone whose mind was somewhere else entirely. Isaac's uncle, William Ayscough, saw what was happening and intervened. Ayscough was a Cambridge graduate himself, a clergyman who recognised that Isaac wasn't lazy or defiant. He was intellectually gifted, completely wasted on farming. Ayscough convinced Hannah to send Isaac back to school, and here's where it gets interesting. Henry Stokes, the headmaster who ran Grantham Grammar School, recognised Isaac's mathematical ability. He'd seen something in this strange, angry boy that others missed. Stokes offered to waive the tuition entirely if Isaac could return. He promised to prepare him properly for Cambridge University. Stokes saw genius where everyone else saw oddness. In 1660, Isaac returned to grammar school at age 17, older than most of the other students, but he didn't care. He threw himself into studies with the same obsessive focus he'd shown building mechanical devices, mathematics, Latin, Greek, theology. He devoured it all. And something else happened at the apothecary's house. Isaac boarded again with William Clark, and the Clark family had a daughter and a stepdaughter, and Isaac apparently became close with the stepdaughter. Her name was Catherine Storer, and she's the only woman Isaac Newton ever showed romantic interest in his entire life. Catherine later said they were intended, which suggested they were engaged or very close to engagement. Newton made doll furniture for her, walked with her in the garden. There was clearly something between them. But when Newton left for Cambridge in 1661, the relationship ended. He never pursued another woman, never married, remained celibate his entire life. The Catherine Storer story is important because it shows Newton was capable of human connection, at least when he was young. But something happened at Cambridge, or in his personality, that closed him off completely. After age 18, he never pursued romance, never married, lived alone for more than 60 years. In June 1661, Isaac Newton arrived at Trinity College, Cambridge, as a subsizar, and this is where his real education began. Now you need to understand what a subsizar was. It was the lowest rank of student at Cambridge. You paid reduced fees by working as a servant to wealthier students. You served them meals, cleaned their rooms, ran their errands. It was a humiliating position, especially for someone as proud as Newton. Imagine Isaac Newton, brilliant, obsessive, convinced of his own special destiny, having to serve breakfast to rich idiots who couldn't solve basic mathematical problems. This experience reinforced Newton's isolation and deepened his contempt for social hierarchies based on birth rather than merit. The official curriculum was worthless. Cambridge in the 1660s was still teaching Aristotelian philosophy, outdated even then, classical languages and rhetoric, traditional logic and ethics. It was basically a medieval education in the middle of the scientific revolution. The scientific revolution was happening elsewhere. Cambridge hadn't caught up. But here's what Newton did. He ignored the official curriculum almost entirely and educated himself. He filled notebooks with his own course of study, reading Descartes, Galileo, Kepler, Boyle, the modern natural philosophers, the revolutionaries, the people who are actually advancing human knowledge. These notebooks are crucial. Newton kept detailed study notes in a notebook titled Questiones Quaedam Philosophicae, certain philosophical questions, and in it he listed topics he was investigating on his own: mathematics, optics, mechanics, astronomy, all self-directed, none of it assigned. These notebooks show his mind developing, show him asking the questions that would lead to his greatest discoveries. And the loneliness continued. He made almost no friends at Cambridge, didn't join any social activities, spent all his time studying alone. His roommate eventually left because Newton was too strange, too obsessive, too difficult to live with. Newton lived in his own world of books and mathematics. Then in 1663, something important happened. Newton encountered a book that would change his life: Euclid's Elements of Geometry, the foundation of all mathematical thinking. And here's what tells you about Newton's arrogance. He initially thought Euclid was too obvious, too simple, and he tried to skip ahead to more advanced topics. Only later did he recognize the genius of Euclid's proofs, and he went back and mastered it completely, teaching himself to think geometrically, teaching himself mathematical rigor. This was Newton learning alone, teaching himself, challenging himself. In 1663, Isaac Newton met the man who would change his trajectory, Isaac Barrow, the Lucasian Professor of Mathematics at Cambridge. Who was Isaac Barrow? He was the first Lucasian professor. The endowed chair had just been created in 1663, and Barrow was appointed. He was a mathematician, theologian, classical scholar, only 33 years old, but already recognised as brilliant. And Barrow was one of the very few faculty members who recognised Newton's genius. Barrow saw immediately that Newton wasn't a normal student. Here was someone who could not just learn mathematics, but extend it, create new mathematics, solve problems that had stumped the best minds in Europe. What Barrow taught Newton: advanced geometry far beyond the curriculum, optics, which was Barrow's specialty, how to think about light and vision, mathematical methods that weren't being taught anywhere else. But more importantly, Barrow gave Newton confidence. The relationship dynamics were interesting. Barrow became the closest thing to a mentor Newton ever had, but it wasn't warm or paternal. It was professional respect, not affection. Barrow recognised Newton's ability. Newton respected Barrow's knowledge, but Newton already believed he would surpass Barrow. And he was right. Barrow would later help Newton get his first fellowship at Trinity College, and eventually, in 1669, Barrow would resign his Lucasian professorship so that Newton could have it. This was extraordinary. Barrow was only 39 years old, giving up a prestigious, endowed chair for his student. But Barrow knew Newton was the greater mathematician, and this set a precedent. This pattern would repeat throughout Newton's life. Newton would find a mentor or supporter who helped him advance, then Newton would surpass them and cast them aside. Barrow was the first, but certainly not the last, because Newton was about to enter the most productive period in the history of science. The plague was coming to Cambridge, and Isaac Newton was going home to Woolsthorpe, where, in 18 months of isolation, he would revolutionise human understanding of the universe. Chapter 3. When physics became exact. For 2,000 years, everyone believed Aristotle's physics, and Aristotle's physics was completely wrong. But nobody could prove it until Newton. Here's what Aristotle taught. Heavy objects fall faster than light objects. Objects in motion naturally come to rest. There's violent motion like throwing a projectile, and natural motion like things falling downward. Everything has a natural place it seeks, and motion requires continuous force. Push a cart and it moves. Stop pushing and it stops. This seemed obviously true. Drop a rock and a feather. The rock falls faster. Roll a ball across the ground, it stops. Throw something in the air, it falls back down. Push a cart, then stop pushing, the cart stops. Common sense, everyday experience supported Aristotle for 2,000 years. Then Galileo started to crack it. Galileo had started to challenge this. He said heavy and light objects actually fall at the same rate. The difference was air resistance. He said objects in motion stay in motion. Friction makes them stop, not some natural tendency toward rest. He rolled balls down inclined planes and measured their acceleration. He was doing experiments, actual measurements, but Galileo had limitations. He could describe motion geometrically. He could measure acceleration, but he couldn't explain why objects accelerate. He had no mathematical law connecting force and motion, no theory of what force actually is. Just observations, not explanation. So here's what was still missing in 1660. There were no mathematical laws of motion, no precise definition of force, mass or acceleration, no way to calculate trajectories exactly, and most importantly, no connection between falling objects and planetary motion. Celestial mechanics, Kepler's laws of planetary orbits, were completely separate from terrestrial mechanics. There was no unified theory. The specific unsolved problems that plagued natural philosophers were these. Why do planets orbit in ellipses? Kepler had observed it but couldn't explain why. What keeps planets moving when there's no air in space to push them? Why doesn't the moon fall to Earth like an apple falls from a tree? How do you calculate the exact trajectory of a cannonball? What is the relationship between force, mass, and motion? And why does everything fall at the same rate regardless of weight? Nobody could answer these questions. Why nobody could solve it? The problem required inventing new mathematics, calculus, to handle continuous change. Nobody had the mathematical tools to describe acceleration, changing velocity, forces that vary with distance. The mathematics didn't exist yet. Someone would have to invent it. And then the plague arrived. In August 1665, bubonic plague swept through Cambridge. The university closed indefinitely. Students dispersed, faculty fled. Newton returned to Woolsthorpe. And in isolation, on a farm in the middle of nowhere, with nothing but time and his thoughts, Isaac Newton would solve all of it. During 1665 and 1666, 18 months of isolation, Newton invented the mathematics he needed and then solved the problem of motion completely. He gave humanity the 3 laws that govern everything that moves. An object at rest stays at rest. An object in motion stays in motion at constant velocity unless acted on by external force. Now you need to understand why this was revolutionary. This contradicted 2,000 years of Aristotelian physics. Rest is not the natural state. Motion doesn't need continuous force to continue. Rest and uniform motion are equivalent states. Only changes in motion need explanation. Before Newton, you had to explain why things move. After Newton, you had to explain why they change motion. This completely inverted the framework of physics. The question wasn't why does it move, but what force changed its motion. Force equals mass times acceleration. This single equation connected force, mass, and motion mathematically for the first time in history. What problem this solved? You could now calculate the exact force needed for any motion. You could predict motion from known forces. You connected cause, force to effect, acceleration, quantitatively. Motion became predictable, calculable, not just describable. This turned physics from philosophy into mathematics. The second law of Newton says, if you know the forces acting on something, you can predict its motion exactly. No ambiguity, no guessing, pure mathematical certainty. And it works for everything. From planets to projectiles, from atoms to galaxies, one equation. For every action, there is an equal and opposite reaction. When you push on something, it pushes back on you with exactly equal force. Why this mattered? It explained how rockets work. Push exhaust gas backward. The exhaust pushes the rocket forward. It explained walking. Push on the ground backward. The ground pushes you forward. It gave us conservation of momentum. It showed that forces always come in pairs. It made forces symmetrical and balanced. What became possible immediately? With these three laws, you could calculate the trajectory of any projectile, predict the outcome of collisions, design machines and structures, understand how every force in the universe works. These laws turned physics from philosophy into engineering. And here's the thing, they're still taught to every physics student today because they're still true. Newton got it right. But to actually use these laws to solve real problems, Newton needed mathematics that didn't exist, so he invented it. And this invention was as important as the laws themselves. Here's the problem velocity and acceleration pose. Velocity is distance divided by time, but that gives you average velocity over an interval. What about velocity at a specific instant? An acceleration is change in velocity. But how do you calculate something that's continuously changing at every moment? If you try to calculate instantaneous velocity, you divide distance travelled by time elapsed. But at a single instant, time elapsed is 0. And you can't divide by 0. Mathematics breaks down. You need a completely new approach. Newton invented what he called the method of fluxions, a way to calculate instantaneous rates of change. He imagined quantities flowing continuously, like water, and calculated their rate of flow at each instant. The key insight was infinitesimals. Newton imagined dividing time into infinitely small intervals, so small they're almost 0. In each tiny interval, the change is basically constant, so you can use simple arithmetic. Then you add up an infinite number of these intervals to get the total motion. This is the foundation of calculus. What calculus allowed you to calculate? Velocity at any specific instant, acceleration, which is the rate of change of velocity, maximum and minimum values, so you could optimize trajectories, areas under curves, which gives you distance travelled, volumes of irregular shapes, any problem involving continuous change. Before calculus, you could describe motion geometrically. Afterward, you could calculate it precisely. You could write an equation for motion and solve it to predict exactly where something would be at any future time. This was completely new. The applications exploded. You could calculate planetary orbits, design optimal trajectories, predict tides, optimize engineering designs, model any changing system. Calculus became the foundation for all physics, all engineering, all economics. Every scientist, engineer, economist uses calculus today. And here's the tragedy. Newton invented calculus in 1665-66 when he was 23 years old, and he told almost nobody for nearly 40 years. The most powerful mathematical tool ever created, and he hoarded it, kept it secret, used it privately, but refused to publish. Because he was paranoid someone would steal credit, and this secrecy would lead to the most bitter disputes in scientific history. But we'll get to that. Chapter 4. One force for heaven and earth. For centuries, astronomers could describe how planets moved, but nobody could explain why they moved that way, until Newton unified heaven and earth with one force, one law. Here's what astronomers knew by 1665. Copernicus in 1543 had shown that Earth and planets orbit the Sun, not the other way around. Kepler's first law from 1609, planets orbit in ellipses with the Sun at one focus, not perfect circles. Kepler's second law, planets sweep out equal areas in equal times as they orbit. Kepler's third law, the orbital period squared is proportional to the distance cubed. And Galileo had shown all objects fall at the same rate regardless of weight. But these were separate, disconnected observations. The questions nobody could answer. Why ellipses specifically? Why not circles or some other shape? What force keeps planets in orbit? Why don't planets fly off into space or crash into the sun? What's the connection between falling apples and orbiting planets? Are the heavens governed by different laws than Earth? Most educated people still believed Aristotelian cosmology, celestial spheres made of perfect, unchanging ether, moving in perfect circles, because circular motion was natural to them. The heavens operated by completely different physics than Earth, or so everyone thought. Kepler himself had discovered the mathematical laws describing planetary motion, but he thought there was a magnetic force emanating from the spinning sun that pushed planets around like a giant rotating magnet. He had discovered the pattern, but completely misunderstood the mechanism. René Descartes proposed that space was filled with invisible fluid vortices swirling around the sun, carrying planets along like leaves in a whirlpool. This was the leading theory in the 1660s. It was completely wrong. In 1679, we'll get to this later, Robert Hooke would pose a question to Newton. What orbit would a body follow if gravity decreased with the square of distance from the sun? Hooke suspected an inverse square law, but he couldn't prove what orbit it would produce. This question would haunt Newton and eventually lead to the Principia. What was needed to solve this? You needed mathematical proof connecting gravity to orbital shape. You needed an explanation of what gravity actually is. You needed unification of terrestrial and celestial mechanics. One force, one law governing both Earth and the heavens. And you needed the mathematical tools, calculus, to prove it. Why nobody before Newton could solve it. You needed calculus to handle forces that change with distance. You needed geometric proof sophisticated enough to convince skeptics. You needed physical insight to realize Earth and heaven follow the same laws. And you needed the arrogance to believe you could overturn 2,000 years of Aristotelian cosmology. Newton had all of these. The story of Newton's apple is probably embellished, but the insight it represents is real. Newton realized the force pulling an apple down is the same force holding the moon in orbit. Newton supposedly was sitting in his garden at Woolsthorpe, saw an apple fall from a tree and wondered, why does the apple fall straight down, but the moon doesn't fall? And then the insight struck. The moon is falling. It's constantly falling toward Earth, but it's also moving sideways so fast that it falls around Earth instead of into Earth. Let me explain the physics of orbital motion. Imagine throwing a ball horizontally. It curves down because gravity pulls it down while it moves forward. Throw it faster, it goes farther before hitting the ground. Throw it fast enough, and the curve of its fall matches the curve of the Earth. It falls around the Earth, never hitting the ground. That's an orbit. The moon is constantly falling toward Earth, but it's moving sideways so fast that it keeps missing. If gravity follows an inverse square law, if force decreases with the square of distance, then the force on the moon should be 1/3600th the force at Earth's surface. Why? Because the moon is 60 Earth radii away, and 60 squared equals 3600, so the force should be 3600 times weaker. Newton calculated how far the moon should fall toward Earth each second if only gravity held it in orbit, using the moon's known orbital radius and period. If his inverse square theory was right, the calculated fall distance should exactly match the observed orbital motion. The numbers matched perfectly. The calculation worked. The moon's actual orbit could be explained completely by Earth's gravity following an inverse square law. This meant terrestrial gravity and celestial motion were the same. One force, one law, no distinction between Earth and heavens. What this unified for the first time in history, falling apples and the orbiting moon, the physics of Earth and the physics of the cosmos, terrestrial mechanics and celestial mechanics, one set of laws for all of nature. Heaven and Earth were no longer separate. Newton proposed that every mass attracts every other mass with force proportional to the product of their masses, divided by the square of distance between them. Force equals gravity, constant times mass divided by distance squared. This single equation explained everything. The sun attracts planets, and planets attract the sun with equal forces. The moon attracts Earth, and Earth attracts the moon. You attract the Earth, and Earth attracts you. Every atom attracts every other atom. Gravity is truly universal, works everywhere identically. The same force explains tides, planetary orbits, falling objects, comets, everything. But Newton, knowing that gravity is inverse square, wasn't enough. He had to prove mathematically that inverse square force produces exactly the elliptical orbits Kepler observed. If gravity follows an inverse square law, what shape orbit does that create? Kepler had observed ellipses empirically. But why ellipses? What about the mathematics of inverse square force produces that specific shape? The force constantly changes as the planet moves. The direction of force constantly changes. The velocity constantly changes. You need to track position and velocity simultaneously. You can't use simple geometry. This requires calculus and advanced geometric proofs. Using his calculus methods and geometric techniques, Newton proved that inverse square central force produces conic section orbits, ellipses if the total energy is negative, circles if the total energy is exactly at the threshold, parabolas if the total energy is exactly zero, hyperbolas if the total energy is positive. The mathematics forced this result. This wasn't arbitrary. This came directly from the inverse square law. This wasn't just observation anymore. This was mathematical proof. It showed Kepler's laws weren't arbitrary. They followed from gravity. They were consequences of the inverse square force law. It connected force law directly to orbital geometry. It explained why ellipses specifically, and it predicted orbits of comets, which follow parabolic or hyperbolic paths. What you could now calculate that was impossible before, the exact orbit of any celestial body given its position and velocity, the effect of perturbations when multiple bodies interact gravitationally, the return of comets. This is how Halley predicted his comet would return. You could calculate the masses of planets from their moon's orbits. You could explain tides from the combined gravitational pull of sun and moon. Everything in the solar system became predictable. Newton had done what nobody in history had done. He'd taken the chaos of celestial motion and reduced it to one force, one equation, one set of laws. The universe operated by mathematics, and humans could understand those mathematics. This was the birth of modern physics. Chapter 5. Light Disassembled. While Newton was revolutionizing mechanics, he was also solving another ancient mystery. What is light, and where do colours come from? The answer would overturn 2,000 years of theory and start his first major feud. Here's what everyone believed about light in 1660. Aristotle's theory. Light is pure and simple. White light is fundamental, basic, unmodified. Colours are modifications of white light. You create colours by mixing darkness with light. More darkness equals deeper colour. This was universally accepted. Nobody questioned it. Every telescope in the 1660s had a serious flaw. Coloured fringes around bright objects, rainbows around stars, blurry, distorted images. The best lens makers in Europe couldn't fix it. This was called chromatic aberration, and nobody understood what caused it. Here's why telescopes had coloured fringes. Lenses bent light to focus it, but different colours bent at different amounts, so the colours didn't focus at the same point. This created coloured halos around images, made telescopes less powerful than they could be. Descartes said light is pressure transmitted through an invisible medium. Hooke said light is rapid vibration or pulse waves. Grimaldi discovered diffraction, but couldn't explain it. Everyone was experimenting. Nobody had a complete theory. And then Newton bought a prism. In 1666, Newton bought a glass prism at a fair and started experimenting in his room at Cambridge. He wanted to understand the nature of light and colour, and what he discovered would change everything. Newton conducted what he called the experimentum crucis, the crucial experiment, and it proved that everything everyone believed about light was wrong. Pass white sunlight through a prism. Light spreads into a rainbow of colours. The spectrum: red, orange, yellow, green, blue, indigo, violet. This was well known, not new. People had been doing this for decades. The traditional interpretation was this. Everyone thought the prism was modifying the white light, changing it into colours, like adding darkness to pure light. The prism was doing something to the light, creating colours that weren't there before. That's what Aristotle said. That's what everyone believed. But Newton did something nobody had thought to do. He took the coloured light from the first prism and passed it through a second prism. If the prism was modifying light, if it was creating colours, then the second prism should modify it further, should change the colour again. But it didn't. Take red light from the first prism, pass it through a second prism, red stays red, doesn't change. Take blue light, pass it through a second prism. Blue stays blue, doesn't change. Each colour was unchangeable, fundamental. White light isn't pure, it's composite. It's a mixture of all the colours mixed together. The prism doesn't create colours, it separates colours that were already there. White is the mixture. Colours are fundamental. This was the exact opposite of what everyone believed. Different colours of light refract, bend at different angles when passing through glass. Red bends the least. Violet bends the most, so a prism spreads white light into a spectrum, separating the colours that were mixed together. This explained everything. Why telescopes had chromatic aberration. Lenses are just shaped glass. Red light focuses at a different point than blue light, so you can't get all colours to focus at the same place. That's what creates the coloured fringes. Now Newton understood the problem. White light is a mixture, not fundamental. Colours are fundamental and cannot be changed. Different colours have different properties, specifically different refraction angles. Light is not simple. It has structure. Aristotle was completely wrong. Understanding chromatic aberration was one thing, solving it was another. And Newton's solution made him famous. If different colours focus at different points, you can't make a perfect lens. You can try different glass types, different shapes, different combinations, but you can't change the fundamental physics. Different colours will refract differently. Don't use lenses at all. Use mirrors. Mirrors reflect all colours equally. No chromatic aberration. Instead of refracting light through glass, you reflect it off a curved mirror. Newton built it in 1668. He was 25 years old. It was only about 6 inches long, used a curved mirror instead of an objective lens, magnified about 40 times. No chromatic aberration, crystal clear images. This solved a problem that had stumped the best instrument makers in Europe. Mirrors could be made much larger than lenses. This opened the path to giant telescopes. Reflecting telescopes became the standard design. All major telescopes today use mirrors. The Hubble Space Telescope, the James Webb Space Telescope, all reflecting telescopes, all based on Newton's design. Newton demonstrated his reflecting telescope to the Royal Society in London in 1672. They were amazed. Here was an unknown young Cambridge mathematician who'd solved chromatic aberration, built a working telescope that outperformed instruments 3 times its size. The Royal Society immediately elected Newton a fellow. He was 29 years old, suddenly famous. The reflecting telescope had made his reputation, and the Royal Society asked him to publish his theory of light and colour. Newton agreed to publish, and this decision to share his work publicly, to expose his ideas to criticism, would lead to the first of his great feuds, and nearly made him quit science forever. Chapter 6. Criticism as Betrayal. In February 1672, Newton published his first scientific paper explaining his theory of light and colour, and the reaction nearly destroyed him. Newton sent a detailed letter to the Royal Society, explained his prism experiments, described his theory of white light as composite, published it in Philosophical Transactions. This was Newton's first public scientific statement. He was 29 years old. At first the reaction was enthusiastic. Royal Society members praised the experimental work. The reflecting telescope had already impressed them. Now here was careful, systematic investigation of light and colour. They elected Newton a fellow. But then Robert Hooke responded. Now you need to understand who Robert Hooke was. Hooke was curator of experiments at the Royal Society, England's leading experimental scientist, an expert in optics, microscopy, mechanics. He was 37 years old with an established reputation. Hooke reviewed Newton's paper, and Hooke wrote a lengthy response that was dismissive and patronising. Hooke said Newton's experiments were interesting, but his conclusions were wrong. Hooke believed light was a wave. Newton's particle theory couldn't explain diffraction, interference, and other phenomena Hooke had observed. But here's the problem. Hooke's tone. Hooke didn't just disagree scientifically, he was condescending. He treated Newton like a promising student who'd overreached. He praised the experiments, but dismissed the theory. He suggested Newton needed to learn more before making grand claims. Newton lost his mind. He couldn't separate scientific criticism from personal attack. He wrote furious multi-page responses defending every detail, attacking Hooke's own theories, demanding apologies. This wasn't scientific discourse, this was war. Why Newton reacted so badly? This was the first time his work was publicly criticised. He perceived Hooke as attacking his competence. He couldn't tolerate anyone questioning him. He saw criticism as theft of credit. His abandonment trauma was activated. Any challenge felt like betrayal. Newton and Hooke exchanged increasingly hostile letters. The Royal Society tried to mediate. Other scientists took sides. Continental philosophers like Christian Huygens also criticised Newton's theory. Newton felt besieged, surrounded by enemies. In 1693, Newton tried to resign from the Royal Society. He claimed he couldn't afford the membership fees, but the real reason was clear. He couldn't stand criticism. He wanted to retreat to Cambridge, to isolation, where nobody could challenge him. The Royal Society refused to accept his resignation. They waived his membership fees, begged him to continue, promised to protect him from harsh criticism. Newton stayed, but he barely participated for years. This first confrontation with Hooke convinced Newton that publishing was dangerous, that sharing work invited theft and attacks. And for the next 15 years, Newton published almost nothing. He worked in secret, hoarded discoveries, and trusted no one. The Principia only exists because Edmund Halley literally begged him to publish. While feuding with Hooke about optics, Newton was pursuing a secret obsession that consumed decades of his life: alchemy. And if anyone had known the extent of it, his scientific reputation would have been destroyed. What was alchemy in the 17th century? It wasn't just about turning lead into gold. Alchemy was the study of matter and transformation, a mix of chemistry, mysticism, and theology. Practitioners used coded language. They believed matter had a spiritual dimension. They searched for the philosopher's stone. Newton spent more time on alchemy than on published physics. He conducted thousands of experiments in a laboratory he built behind his Cambridge rooms, heating metals for months, observing reactions, recording everything in coded notebooks. And he filled over 1 million words of notes on alchemy, more than everything else he wrote combined. Newton built furnaces and worked at night, melted and mixed metals for months: mercury, lead, antimony, sulfur. He observed colour changes, meticulously recorded temperatures, times, reactions, the same scientific rigour as his physics. Newton wasn't trying to get rich making gold. He was seeking the fundamental structure of matter. He believed alchemical texts encoded ancient wisdom about nature's deeper secrets, about how matter transforms, about hidden forces between particles. Newton kept his alchemy completely secret. Alchemy was legal, but disreputable, associated with frauds and mystics. If Cambridge authorities or the Royal Society knew the extent of Newton's alchemical obsession, they would have questioned his rationality. So he worked behind locked doors, at night, told nobody. For Newton, alchemy and physics were the same project. Both sought to understand forces in nature. Gravity acted between planets. Alchemical forces acted between particles. Both were trying to decode God's design of matter and motion. Newton's alchemical experiments exposed him to enormous amounts of mercury vapour. Analysis of Newton's hair shows mercury levels 40 times normal. Mercury causes paranoia, mood swings, tremors, personality changes. This may explain Newton's later mental instability. Modern scientists want to separate rational Newton from mystical Newton, but you can't. The same obsessive, secretive mind that discovered gravity also spent decades trying to transmute metals. Both came from Newton's belief that nature held hidden mathematical and spiritual truths waiting to be decoded. From 1673 to 1679, Newton essentially disappeared from the scientific community. He published nothing, feuded with no one, worked in complete isolation. What Newton was doing in these silent years: alchemy experiments, extensive work, biblical chronology studies, theological research, especially anti-Trinitarian views. Some mathematics, mostly kept private. Some optics, never published. Mostly, we don't fully know. Newton's isolation became almost pathological. He lectured to empty rooms at Cambridge. Students stopped attending because his lectures were incomprehensible. Advanced mathematics delivered in monotone to an empty hall. He didn't seem to care or even notice. Newton lived in his rooms at Trinity College, worked alone, ate irregularly, walked in the garden absorbed in thought. He forgot appointments, meals, sleep. Servants found him standing in the same spot hours later, having not moved. He existed entirely in his own mind. For 6 years Newton published nothing, answered almost no letters, attended no Royal Society meetings. He'd withdrawn completely from the scientific community. The world's greatest living scientist, and nobody knew what he was working on. But forces were building that would pull Newton back. Robert Hooke was working on planetary motion, trying to explain orbits mathematically. And in 1679, Hooke would make the fatal mistake of contacting Newton, asking for his ideas about orbital mechanics. The letter that changed everything. Hooke's 1679 letter asking Newton about inverse square gravity would lead directly to the Principia, to Newton's greatest achievement, and to a feud that would last until one of them died. Chapter 7. Writing the Laws of Reality. In August 1684, a young astronomer named Edmund Halley travelled to Cambridge to ask Newton a simple question, and that conversation led to the greatest scientific work ever written. January 1684, Halley, Hooke, and architect Christopher Wren were meeting in a London coffee-house, discussing the great, unsolved problem of their time. What force law produces elliptical orbits? Robert Hooke claimed he'd proven that an inverse square law produces ellipses, but he couldn't show the proof. Wren offered a prize, a 40-shilling book, to whoever could produce the proof. Hooke promised he'd produce it. Months passed. Hooke produced nothing. So Halley travelled to Cambridge. Halley asked Newton, what orbit would a planet follow under inverse square gravity? Newton immediately replied, an ellipse. Halley was stunned. How do you know? Newton said, I've calculated it. Newton looked through his chaotic piles of papers, but couldn't find the proof, so he casually promised to send it to Halley later. Halley left Cambridge amazed, but unsure if he'd ever actually see this proof. Newton worked intensely for 3 months. Didn't just recreate the old proof, he expanded it into a complete treatise. De motu corporum in gyrum, on the motion of bodies in orbit. 9 pages of revolutionary physics. He sent it to Halley in November 1684. When Halley read it, he realised this wasn't just proof of elliptical orbits. This was the foundation for an entirely new physics. Newton had derived the laws of motion, the law of universal gravitation, the mathematics to describe the entire solar system. This had to be published immediately. But Newton didn't want to publish. He feared criticism, feared priority disputes, didn't think anyone would understand, wanted to keep working privately. Publishing meant exposure, vulnerability. Edmund Halley spent the next 2 years begging, convincing, cajoling Newton to expand De Motu into a full book. Halley offered to pay for printing himself, to edit the manuscript, to handle all correspondence, to shield Newton from criticism. Halley understood Newton was difficult, but the work was too important to lose. In 1685, Newton agreed to write the complete treatise, but on his terms. He would write in Latin, make it deliberately difficult, not answer critics, not attend discussions, take it or leave it. From 1685 to 1687, Newton worked with frightening intensity, writing Philosophiae Naturalis, Principia Mathematica, the mathematical principles of natural philosophy. And what he produced changed human understanding of reality. Book 2, Motion in Ideal Space. This is the pure theoretical framework. Newton defines mass, force, momentum, inertia. He states the 3 laws of motion, gives mathematical treatment of motion in a vacuum, how bodies move under various force laws, central force motion like planets, and here's the crucial part. He derives Kepler's laws from gravity, shows that Kepler's observations aren't arbitrary. They follow mathematically from inverse square gravity. Book 2, Motion in Resisting Mediums. This covers motion through fluids and gases, resistance and drag forces, wave motion in fluids, speed of sound calculation. But most importantly, Newton demolishes Descartes' vortex theory. He proves mathematically that space cannot be filled with fluid push-in planets around. Space must be a vacuum. Book 3, The System of the World. This applies bookwork theory to the actual solar system. Newton explains the moon's orbit precisely, explains tides from the combined gravity of sun and moon, predicts comet orbits, calculates the masses of the sun and planets, explains the precession of the equinoxes. He shows the entire cosmos operates by the same laws. What the Principia actually proved for the first time. It derived Kepler's 3 laws from universal gravitation, showed they weren't observations, but mathematical consequences. It explained ocean tides mathematically. Both the sun and moon pull on Earth's water, creating the tidal patterns. It predicted the return of comets. Halley used Newton's methods to predict his comet would return in 1705, and it did. It calculated the relative masses of planets from their moon's orbits. It explained why Earth is an oblate spheroid, bulges at the equator because of rotation. It explained the precession of the equinoxes, the wobble of Earth's axis over thousands of years. It predicted perturbations in planetary orbits from their mutual gravitational attraction. Newton wrote the Principia in Latin, using classical geometric proofs instead of his calculus, partly because geometric proofs were more accepted by traditionalists, but mainly to keep out what he called little smatterers in mathematics. Newton didn't want casual readers. Written in Latin, the international scholarly language, used geometric proof as not algebra. No calculus notation anywhere, even though Newton used calculus to discover the results. It assumed advanced mathematical background, was dense, terse, offered no hand-holding. The proofs required weeks to work through. When Principia was published, maybe 100 people in all of Europe could fully understand it. Even leading mathematicians struggled. It required mastery of geometry, physics, and enormous intellectual effort. This was intentional. Newton wanted only the most serious minds engaging with his work. As Newton neared completion of the Principia, disaster nearly struck. Robert Hooke heard about the book and claimed he deserved credit. Hooke said his 1679 letter had given Newton the inverse square idea, demanded acknowledgement in the book, claimed Newton had stolen his theory. He threatened a public dispute, wanted his name in the Principia. Newton completely lost control. He threatened to suppress the entire third book of Principia rather than give Hooke any credit. He wrote furious letters to Halley, saying he'd rather burn the manuscript than acknowledge Hooke. Poor Halley was caught between two angry men, had to keep Newton from destroying the book, had to mollify Hooke. Halley begged Newton to continue, promised to handle Hooke. Newton agreed to finish the book, but he removed every single mention of Hooke's name, systematically erased him. He added a scholium claiming he'd had the inverse square idea before Hooke's letter. He gave credit to Wren and Halley instead, systematically erased Hooke from the narrative. In July 1687, Philosophia Naturalis Principia Mathematica was published in Latin, 511 pages, paid for entirely by Edmund Halley, who also edited it, corrected proofs, handled printing, defended Newton from critics. Without Halley's intervention, Principia wouldn't exist. Halley paid for printing himself. The Royal Society had no money. It cost him a significant portion of his salary. He received no compensation. He did it because he understood the importance. Sometimes genius needs a handler. Halley was Newton's handler. Chapter 8. The Price of the Principia. After Principia was published, Newton was the most famous scientist in Europe, but he was also physically and mentally destroyed. The effort of writing it had pushed him past human limits. Newton was 44 years old in 1687, dramatically underweight from not eating. Hair turned grey during the writing. Chronic insomnia, tremors in his hands, eyes bloodshot from overwork. Principia revolutionized physics almost immediately. The best mathematicians in Europe, Christian Huygens, Gottfried Leibniz, the Bernoulli brothers, recognized its importance, though many struggled to understand it. Newton was now the most celebrated natural philosopher alive. But Newton wasn't celebrating. He was deeply depressed after publication, exhausted mentally and physically, felt exposed and vulnerable. He didn't enjoy the fame, wanted a retreat again, stopped all mathematical research. Newton abandoned physics and mathematics completely, returned to his secret alchemical experiments, to biblical chronology, to theological studies. This would be the pattern for the rest of his life. Bursts of incredible productivity followed by complete withdrawal. Newton had been at Cambridge for 26 years, living in rooms at Trinity College, lecturing to empty halls, working in isolation. And he was done with it. He wanted out. He wanted a position in London, government service, a different life, anything to escape Cambridge. Newton actively sought political appointments, used his fame from Principia to make connections, applied for various government positions. He hoped for a position at the Royal Mint or some government office. All applications initially failed. This frustrated him enormously. By 1693, Newton was under crushing stress. Principia was finished, but he had no new project. The fame brought unwanted attention. Critics asked questions he didn't want to answer. He was stuck at Cambridge, desperately wanted to leave, and his mental state was deteriorating badly. In the summer of 1693, Isaac Newton had a complete mental breakdown, and for several months his friends feared he'd gone permanently insane. Summer 1693. Newton stopped sleeping entirely, barely ate for weeks, maybe months, lost significant weight. He showed signs of severe paranoia, wrote bizarre accusatory letters to friends, accused them of plotting against him. September 13th, 1693. Newton wrote to Pepys, the diarist and government official, "I am extremely troubled at the embroilment I am in, and have neither ate nor slept well this 12-month, nor have my former consistency of mind. This from the man who wrote Principia. Far worse was Newton's letter to philosopher John Locke. Newton accused Locke of trying to embroil him with women, said he wished Locke were dead, wrote that he'd been so disturbed when they met that he wished he'd never known him. Locke was shocked and terrified. Locke wrote back concerned and confused, asked what he'd done to offend, offered friendship and help, treated Newton with kindness. After a few months, Newton recovered enough to write apologising to Locke and Pepys. He said he'd been ill, distempered by sleep deprivation, not himself. He blamed insomnia, but offered no other explanation. Locke graciously forgave him, but privately worried about Newton's sanity. Possible mercury poisoning from decades of alchemy. Analysis of Newton's hair shows 40 times normal mercury levels. Exhaustion from years of overwork. Stress from seeking failed appointments. Underlying mental illness, possibly bipolar disorder. Extreme sleep deprivation, compounding everything. Isolation and loneliness. Rumours spread across Europe that Newton had gone mad, some said permanently. Leibniz heard Newton had broken. The Royal Society debated whether Newton could continue as Fellow. For several months, nobody knew if Newton would recover. By early 1694, Newton seemed back to normal, wrote apologising, blamed illness, resumed some correspondence, but he was fundamentally changed. Something had broken. After the 1693 breakdown, Newton essentially stopped doing original mathematics and physics. At age 50, his creative period was over. No more original mathematics, no new physics discoveries, no major theoretical work. The genius years were finished, 1665 to 1687, the revolutionary period, 1693 to 1727, consolidation, administration, feuds. The mental breakdown had frightened him. The exhaustion was too deep. He feared his own mind couldn't risk another collapse. It was easier to administrate than to create. More alchemy. He continued until late in life. Biblical chronology intensified. Editing and defending Principia, seeking political appointments, later running the Royal Mint, feuding with rivals. We have to wonder what Newton might have discovered if he'd stayed mentally stable. If he'd continued working on fundamental physics and mathematics from 1693 to 1727. That's 34 more years. What problems could he have solved? But perhaps it was inevitable. Newton had burned out completely. Principia had taken everything he had. The mental breakdown was the bill coming due. You can't work 18-hour days for years, ignoring sleep, food, health, and not pay the price. Newton desperately wanted to leave Cambridge, to escape to London, to have a different life. And in 1696, he finally got his chance, appointment as Warden of the Royal Mint, and he left Cambridge forever. Chapter 9. From Laws of Nature to Laws of Men. When Newton arrived at the Royal Mint in 1696, England was in the middle of a currency crisis that threatened to collapse the economy, and Newton solved it through sheer obsessive focus. English silver coins were clipped, worn, underweight. People had been shaving edges off coins, clipping for decades. They melted the silver, kept it. Coins were worth less than face value. This created massive inflation. Economic chaos was spreading. Old coins were hand-struck with rough edges. You could shave a little silver off the edge, file it smooth. The coin still looked normal, but weighed less. Multiply this by millions of coins, and massive amounts of silver were being stolen from the currency. The government ordered all old coins called in to be melted, strike completely new coins with milled edges. Milled edges couldn't be clipped because the grooves would show any tampering. Replace the entire money supply. Had to be done fast to prevent economic collapse. The government ordered every coin in England replaced. This meant melting down millions of coins, striking millions of new coins, with modern technology that prevented clipping, and doing it fast enough to keep the economy functioning. It was an unprecedented logistical challenge. This was usually a ceremonial position, well paid, little actual work required. Previous wardens barely showed up, collected salary, delegated everything. Everyone expected Newton would do the same. Everyone expected Newton to treat it as a sinecure, collect salary, appear occasionally, leave the work to subordinates. Instead, Newton showed up every day, took complete control, revolutionized the entire operation. He arrived at the Mint and took charge personally, extended working hours to 24-hour operation, hired additional workers, increased the number of furnaces, streamlined the production process, installed rigorous quality control, the same obsessive attention to detail as his physics. Under Newton's management, the Mint produced over $100,000 worth of silver coins per week, far exceeding any previous production. The Great Recoinage was completed successfully in 3 years, largely due to Newton's relentless efficiency. England's currency was stabilised. In 1699, Newton was promoted to Master of the Mint, one of the most powerful positions in government. Controlled England's money supply. Substantial salary, $2,000 per year. Real political power. Newton had escaped Cambridge forever. But Newton's most shocking work at the Mint wasn't administrative. It was hunting counterfeiters. And he pursued them with a vindictiveness that reveals his darkest nature. Counterfeiting was widespread. Criminals made fake coins. The penalty was death by hanging. But convictions were rare. Counterfeiters operated almost openly, bribed officials, intimidated witnesses. Newton decided to personally destroy London's counterfeiting networks. He didn't delegate this. He conducted interrogations himself, visited prisons, went undercover in taverns to gather evidence, prosecuted cases. This wasn't normal for a mint master. He personally interrogated suspects in prison, offered deals to informants, reduce your sentence for testimony, built cases meticulously over months, used a network of spies and paid informants, tracked down entire criminal networks, prosecuted relentlessly in court. Newton's most famous case was against William Challoner, a brilliant counterfeiter who'd been operating for years. Challoner was clever, charismatic, had bribed his way out of prosecution multiple times. He even petitioned Parliament, claiming the Mint's coins were poorly made. Challoner's attack on the Mint infuriated Newton, challenged Newton's competence publicly. Newton couldn't let that stand. He became obsessed with destroying Challoner, spent years building the case. Newton gathered overwhelming evidence, tracked down Challoner's accomplices, broke the network with informants, multiple witnesses, detailed records. Challoner was arrested in 1699, tried and convicted, hanged at Tyburn in March 1699. Newton prosecuted Challoner with the same intensity he'd shown in his feuds with Hooke and Leibniz. Once Newton identified an enemy, he was relentless, systematic, merciless. He couldn't let go. Some historians say Newton attended Challoner's execution to watch him hang. This is who Newton was. Newton sent dozens of counterfeiters to the gallows, personally oversaw over 100 prosecutions, succeeded in most of them. He broke London's counterfeiting networks through fear and systematic prosecution. applied the scientific method to law enforcement. By 1700, Isaac Newton had transformed from isolated genius to wealthy, connected, powerful member of the establishment. Master of the mint salary was $2,000 per year, enormous for the time, plus percentage of coin production, plus fees and allowances. Newton became genuinely wealthy, invested wisely mostly. Left an estate worth over $30,000 at death. Newton lived well in Jermyn Street, London, later moved to St Martin Street. His niece Catherine Barton kept house. Dinner parties and social gatherings, connections to politicians and aristocrats. A respectable establishment figure. Newton's niece Catherine was beautiful, charming, and intelligent. She managed his household, hosted his dinner parties, became famous in London society. She possibly had an affair with Lord Halifax, though this was never proven. She made Newton's house a social centre. The lonely, isolated, obsessive genius of Cambridge was gone, replaced by a wealthy government official who attended parties, networked with powerful men, lived comfortably. Newton had two completely different lives, but the core personality remained. He still couldn't stand criticism, still feuded with rivals viciously, still jealously guarded priority, still vindictive toward enemies. Now he had real institutional power to hurt them. In 1703, Robert Hooke died, finally removing Newton's greatest obstacle, and Newton immediately became president of the Royal Society, the position he coveted for years but couldn't have while Hooke lived. Now with Hooke dead, Newton would dominate the society for the next 24 years. Chapter 10. The Calculus War. While Newton was running the mint, a brilliant German mathematician named Gottfried Wilhelm Leibniz published his version of calculus, and Newton became convinced that Leibniz had stolen it. He was a German philosopher, mathematician, polymath, invented calculus independently in the 1670s, published first in 1684 and 1686, used different notation than Newton, x del y instead of Newton's dots, different conceptual approach, but got the same results. Leibniz's calculus used notation like di dex for derivatives, the integral sign for integrals. This notation was superior to Newton's dot notation, made calculations clearer, easier to manipulate, led to new discoveries, and it's the notation we still use today. Initially, Newton seemed unconcerned publicly, acknowledged Leibniz's work in letters, didn't claim priority publicly at first, but privately he was furious, believed Leibniz must have stolen it somehow. Leibniz visited London in 1676, saw some mathematical papers, corresponded with English mathematicians. He definitely knew Newton had some method, but there's no evidence he saw Newton's actual calculus manuscripts. Leibniz's approach was different enough to suggest independent discovery. Newton invented calculus first, 1665-66. Leibniz invented it later, 1673-76. But Leibniz published first. 1684. Newton kept his secret for decades. Their notations were different. Their conceptual approaches were different. Both had valid claims, but Newton's psychology couldn't accept this. Newton invented calculus first. He knew he was first. He'd used it privately for 20 years. But because he refused to publish, Leibniz got the credit. Newton saw this as theft, as plagiarism. His paranoia and ego couldn't allow that someone else could independently discover what he'd discovered. For years, Newton said nothing publicly. He stewed in resentment, watched Leibniz's calculus become the standard in Europe, saw continental mathematicians using Leibniz's notation, giving Leibniz credit, calling it Leibnizian calculus, and Newton's rage built. In 1699, a Swiss mathematician loyal to Newton publicly accused Leibniz of plagiarism, and the most bitter priority dispute in scientific history exploded. He was a young Swiss mathematician who became obsessively attached to Newton in the 1690s, possibly Newton's only close friend. The relationship was intense, possibly romantic. Historians still debate this. Fatio worshipped Newton unconditionally. Fatio published a mathematical paper with a preface claiming that Leibniz had stolen calculus from Newton, that Newton was the true inventor, that Leibniz was a plagiarist. Leibniz was shocked and outraged, demanded Fatio prove it or retract. He denied stealing anything, showed his independent development, pointed to his publications, demanded an apology from Fatio, asked the Royal Society to investigate, believed the truth would vindicate him. Fatio had no real evidence, but Newton backed him privately, encouraged him, wrote letters supporting the accusation, but Newton didn't make a public statement yet. He let Fatio do the dirty work. When Leibniz asked the Royal Society to investigate, Newton was president of the society. So Newton appointed the investigation committee himself, chose only people loyal to him, controlled the entire process. All members chosen by Newton, all biased toward Newton. Newton himself secretly wrote the committee's report. The report concluded Leibniz plagiarized Newton, published as official Royal Society judgment, completely one-sided. The committee's report was called Commercium Epistolicum, Commercial Correspondence, published in 1713. It contained letters and documents, supposedly proving Newton's priority. But Newton had selected what to include, edited the presentation, wrote the conclusions himself. It was flagrantly biased. He wrote detailed rebuttals, showed his independent development, pointed out the committee's bias, published his own account. But Newton controlled the Royal Society. In England, Newton's version became official truth. Continental mathematicians saw through Newton's manipulation. They recognized Leibniz had invented calculus independently. Most European mathematicians sided with Leibniz. British mathematicians sided with Newton. It became a nationalistic dispute, England versus the continent. And here's the most pathetic part. Newton wrote anonymous reviews of the Commercium, praising Newton, attacking Leibniz, writing about himself in the third person as an objective observer. He reviewed his own secretly written report anonymously. This is how insecure Newton was. The calculus war consumed Leibniz's final years, destroying his health and reputation until his death in 1716. It consumed the last decade of his life, trying desperately to defend his honour, writing rebuttals nobody in England read, watching Newton systematically destroy his reputation. His health deteriorated from the stress. He died bitter and exhausted in November 1716. When Newton heard Leibniz had died, he reportedly said he'd broken Leibniz's heart. Not with regret, but with satisfaction. Newton had won, had destroyed his enemy, outlived him, and felt triumphant. Modern historians agree both Newton and Leibniz invented calculus independently. Newton first, 1665, but in secret. Leibniz later, 1675, but published. They both deserve credit. Both made genuine independent discoveries. But Newton couldn't share credit, couldn't acknowledge that someone else could achieve what he achieved. British mathematicians used Newton's inferior notation. Continental mathematicians used Leibniz's superior notation. Leibniz's notation dx dy was clearer, more powerful, led to easier discoveries. British mathematics fell behind for a century. Continental mathematicians like the Bernoullis, Euler, Lagrange advanced rapidly. British mathematics stagnated until the 1820s, all because of Newton's ego and nationalism. The calculus war shows Newton at his absolute worst. Brilliant but petty, powerful but insecure. Willing to use institutional power to destroy a rival, willing to lie, manipulate, and cheat to claim sole credit. The same mind that understood universal gravitation couldn't understand basic human decency. Chapter 11. The Heretic. While Newton was feuding publicly with Leibniz, he was hiding a secret that could have destroyed his career. Newton didn't believe in the Trinity, which made him a heretic by every Christian standard of his time. It was an early Christian heresy from the 4th century, taught by Arius of Alexandria. It denied that Jesus was equal to God, believed Jesus was created by God, not co-eternal with God. Declared heresy at the Council of Nicaea in 325 AD. Holding Arian views in Newton's England was dangerous. Newton had studied the Bible intensively in Hebrew and Greek, traced textual variations, analysed early church documents, and concluded that the Trinity was a 4th century corruption added to Christianity. It wasn't in the original scripture. It was imposed by Constantine and church councils. God the Father alone is eternal and supreme. Jesus is the Son of God, but not God himself. Jesus was created by God before all things. The Holy Spirit is not a person, but God's power. The Trinity doctrine was a corrupted addition to Christianity. The early church didn't believe in the Trinity. England was officially Trinitarian Christian. The Trinity was core doctrine, required belief. Denying the Trinity was blasphemy. Newton held positions requiring Anglican orthodoxy, could lose his Cambridge fellowship, could lose his mint position, social and professional ruin, possible legal persecution. Newton wrote hundreds of thousands of words on theology, detailed anti-Trinitarian arguments, biblical textual analysis, historical research on early Christianity, and he published exactly none of it. He kept it locked away, showed it to almost nobody. Over 1 million words on theology, more than all his physics combined. Commentaries on Daniel and Revelation, biblical chronology, history of early church corruption, analysis of prophecy, all kept completely secret. Newton, who demanded credit and recognition for every scientific discovery, hid his theological work completely. He wanted fame for physics, but total anonymity for theology, because physics brought glory, but theology brought danger. One of Newton's strangest obsessions was interpreting biblical prophecy and trying to date the apocalypse. This wasn't casual interest, this was serious intellectual work. Detailed analysis of the book of Daniel, interpretation of the book of Revelation. He believed prophecies were encoded messages from God, tried to match prophecies to historical events, calculated dates of future apocalyptic events, believed he could decode God's plan for history. Newton approached prophecy like physics. He looked for mathematical patterns, symbolic codes, hidden meanings. He believed God had encoded truth in biblical prophecy, just as God had encoded mathematical laws in nature. Both were divine communication, titled The Chronology of Ancient Kingdoms Amended. It attempted to create a precise timeline of biblical history, used astronomical calculations to date ancient events, analysed eclipses mentioned in ancient texts, compared different historical sources, tried to reconcile biblical and secular history. He believed accurate chronology would reveal the divine plan. Thought history showed God's providence operating, wanted to prove biblical history was accurate, believed ancient civilizations had encoded wisdom. This was as important to him as physics. It contradicted, accepted ancient history, placed the fall of Troy 500 years later than traditional dating, rearranged Egyptian dynasties, challenged established biblical chronology, made wild assumptions, forced evidence to fit conclusions. Newton didn't want to publish his chronology, but a manuscript was stolen and published in France without his permission. Newton was furious, wrote a corrected version, published in 1728 after his death. But it was widely mocked. Historians thought it was nonsense. For Newton, physics, alchemy, and biblical study were all one project, all seeking to understand God's design. The universe operated by mathematical laws because God designed it that way. Biblical prophecy followed patterns because God ordained them. Newton sought unified knowledge, divine truth expressed in mathematics and scripture. Modern scholars argue we can't separate Newton, the scientist, from Newton, the alchemist and theologian. He was one person with one integrated worldview, understanding God's creation in all its aspects. Physics revealed God's laws for matter and motion. Alchemy revealed God's laws for transformation of substances. Theology revealed God's plan for human history. Mathematics was the language God used. All were studying the same divine design. Newton believed God was fundamentally mathematical. That divine truth could be expressed in numbers, ratios, geometric patterns. This is why he looked for mathematical patterns in biblical prophecy, the same mindset as finding mathematical laws in physics. Newton believed ancient people possessed knowledge that was later lost or corrupted. The Hebrews, the Egyptians, the Greeks all had partial understanding of divine truth. Newton was trying to recover and complete that ancient wisdom. His physics came from his religious worldview. His belief in mathematical laws came from his belief in a mathematical God. His certainty came from seeing himself as chosen to decode creation. His secrecy came from protecting his heretical theological views. You can't understand the science without understanding the theology. For 200 years, historians tried to save Newton's reputation by separating good Newton, the scientist, from bad Newton, the mystic. But they're inseparable. The genius who discovered universal gravitation also believed he could decode the Book of Revelation. Both came from the same brilliant, obsessive, messianic mind. Chapter 12. President of the Royal Society. From 1703 until his death in 1727, Newton ruled the Royal Society as an absolute dictator. He demanded total loyalty, punished dissent, and used the society as a weapon against his enemies. Robert Hooke died in March 1703. Hooke had been an obstacle for decades. With Hooke dead, the path was clear. Newton was elected president in November 1703. He would hold the position for 24 years until his death, and he transformed the society completely. He attended every single meeting personally, controlled which papers were read, decided what experiments were performed, appointed all committees with his loyalists, vetoed any decision he disliked, tolerated zero opposition or criticism. Under Newton's presidency, the Royal Society became less about advancing science and more about glorifying Newton. Meetings discussed his work, his theories, his priority disputes, his battles. Anyone who questioned Newton was frozen out, exiled from the scientific community. One of Newton's first acts as president was moving the Royal Society to a new building. During the move, the only known portrait of Robert Hooke disappeared. Many historians believe Newton destroyed it deliberately, erasing his old enemy from history visually. All of Hooke's experimental apparatus also disappeared. Newton removed Hooke's name from everything possible. Astronomer Royal John Flamsteed had stellar observations Newton wanted for his lunar theory. Flamsteed refused to share incomplete data. Newton used his power as president to force publication of Flamsteed's data without his permission. He appointed a committee to review Flamsteed's work. The committee ordered Flamsteed to hand over all observations. Newton personally edited Flamsteed's data, published them without Flamsteed's consent in 1712, removed Flamsteed's name as primary author. Flamsteed was devastated, humiliated. Flamsteed eventually got most of his manuscripts back and personally burned 300 copies of Newton's unauthorized edition, but the damage was done. Newton had demonstrated he'd abuse institutional power ruthlessly to get what he wanted. Identify what Newton wanted: data, priority, recognition. Use Royal Society power to get it. Destroy anyone who resisted. Justify it as serving science. But really, it was serving Newton's ego. Newton was the greatest scientist alive. His Principia was transforming physics. His word was law. People were genuinely afraid of him. He could destroy careers, ruin reputations. Better to submit and stay in his favour than resist and be crushed. In 1704, Newton finally published his work on optics, experiments and theories he'd developed 35 years earlier, and only because Robert Hooke was dead and couldn't criticise it. It described his prism experiments from the 1660s, his theory of light and colour developed during the plague years, work on diffraction, reflection, refraction, experiments on thin films creating what we now call Newton's rings, queries about the nature of light and matter. Newton had this work essentially ready since the 1670s, but refused to publish while Hooke lived. He couldn't stand the thought of Hooke criticising it, so he waited literally decades until Hooke died in 1703, then rushed optics to publication in 1704. Think about this. Newton deprived the scientific community of major work on optics for more than 30 years. Because of personal animosity. He'd rather keep revolutionary discoveries secret than risk one man's criticism. This is pathological. Principia was mathematical, Latin geometric proofs, difficult. Optics was experimental, English, accessible, easier to read. Principia was for mathematicians. Optics was for a broader audience. Optics was more widely read initially. The most influential part of optics was the queries at the end. Questions Newton posed about light, matter, atoms, forces. He used the queries to speculate without having to prove anything. A clever way to share ideas without being held to strict standards. Are light and matter interconvertible? Do small particles attract each other? Is space filled with aether? What is the nature of heat? These questions shaped 18th century physics research. Newton appended 2 mathematical treatises to optics, including his first published account of his calculus method. This was 1704, nearly 40 years after he invented calculus, published now solely to establish priority against Leibniz. Even Newton's publication timing was about feuds. Optics influenced 18th century science enormously. The experimental method, the particle theory of light, the speculative queries about atoms and forces, all shaped natural philosophy for generations. By 1710, Newton was approaching 70 years old, the undisputed master of British science, wealthy, powerful, honoured, and increasingly isolated and bitter, knighted by Queen Anne in 1705. Sir Isaac Newton now, first scientist ever knighted for scientific work. Tremendous social prestige. But it fed his already massive ego. He attended royal court events occasionally, socialised with aristocracy, dressed fashionably in expensive clothes, wore elaborate wigs, the fashion of the time, played the gentleman. Far from the isolated Cambridge scholar, the man who'd lived in near total isolation for decades at Cambridge now craved social recognition. The reclusive genius became a courtier. The misanthrope attended parties. Newton had become establishment, what he'd once despised. But the feuding never stopped. The calculus war with Leibniz intensified. New disputes with other mathematicians. Arguments over priority on everything. Continued battle with Flamsteed over the star catalogue. He never stopped fighting enemies. His vindictiveness never diminished. Despite the social appearances, Newton remained fundamentally alone. He never married, never had children. His closest relationship was with his niece Catherine, who managed his household. His friendships were shallow and political. When he died, relatively few mourned the person. They mourned the icon. Newton would live another 17 years, growing wealthier, more honoured, more powerful, but also more rigid, more dogmatic, more convinced of his own infallibility. The last phase of his life would be consolidation, defence of his legacy, and continued warfare against anyone who challenged him. Chapter 13. The Declining Years. In 1720, Isaac Newton made a rare public mistake. He got caught up in the South Sea bubble investment mania and lost a fortune, proving that even genius doesn't guarantee wisdom in all domains. A trading company formed in 1711 with a government-backed monopoly on South American trade. The stock price rose dramatically in 1720. Massive speculation fever gripped England, a classic financial bubble that would collapse catastrophically. Newton bought South Sea Company stock early in the bubble, made substantial profit, sold wisely. Then here's where his genius failed him. He watched the stock keep rising, watched other people getting rich, and bought back in at the peak, near the top of the market. August 1720, the bubble burst. Stock collapsed from 1,000 to 150. Thousands of investors were ruined. Newton lost approximately $20,000, about $3 million in today's money, a significant portion of his wealth. After the disaster, Newton supposedly said, "I can calculate the motions of heavenly bodies, but not the madness of people." This rare admission shows Newton understood he'd been foolish, that his genius had limits, that markets don't follow mathematical laws. It shows Newton was human after all, subject to the same cognitive biases as anyone. FOMO, fear of missing out, affected even him. His mathematical genius didn't extend to finance. Emotional reasoning overpowered logic. Newton was fortunate enough to absorb the loss. He still had his mint salary, his other investments. He recovered financially, though not completely. But the embarrassment stung. Newton hated being wrong, hated admitting mistakes. The South Sea loss was public, humiliating, undeniable. You'd think this experience would humble Newton, would make him more cautious about certainty in non-mathematical domains. But it didn't. Newton remained absolutely certain about his physics, his priority, his interpretations. In everything except finance, his hubris was undiminished. Even in his 70s, Newton continued feuding with anyone who challenged him. His capacity for grudges never diminished with age. Leibniz died in November 1716, but Newton kept attacking his memory, published more anti-Leibniz material, wrote anonymous attacks on a dead man, couldn't let it go even after total victory, needed absolute vindication. Newton published an expanded second edition of the Commercium in 1722, 6 years after Leibniz's death, still trying to prove his priority, still attacking a dead man's reputation. This was Newton at 79 years old, still consumed by a 20-year-old feud. Continental mathematicians who defended Leibniz, anyone who praised Leibniz's notation. John Flamsteed, the ongoing battle over the star catalogue. Anyone who questioned Newton's priority on anything. The list of enemies never stopped growing. Each challenge felt like the original abandonment. His mother choosing someone else. Critics choosing rivals over him. Newton had to win completely, totally. Total victory or total failure. No middle ground was possible. Newton's feuds and his absolute control of the Royal Society severely damaged British science. His followers were terrified to contradict him, afraid to explore ideas that conflicted with Newton's, afraid to make original contributions that might upset him. Continental mathematicians advanced rapidly. The Bernoullis, Euler, Lagrange, making new discoveries. British mathematics stagnated. British scientists stuck defending Newton, fell behind for a century, all because of Newton's ego. Newton demanded absolute loyalty from his followers. Anyone who suggested modifications to his theories, questioned his priority, or praised rivals was cast out of the scientific community. The Royal Society became an echo chamber. Everyone repeating Newton, nobody daring to advance beyond him. As Newton aged into his 70s, he gradually withdrew from social life again. The dinner party stopped, the court appearances ended. He spent more time alone in his house, working on theology and chronology. The brief social period was over. The fundamental isolation reasserted itself, the pattern of his whole life. In his final years, Newton saw himself as guardian of absolute truth in both science and theology, and anyone who challenged his truths was not just wrong, but evil. Still writing on biblical prophecy into his 80s, refining his chronology of ancient kingdoms, developing anti-Trinitarian arguments, but still totally secret, still unpublishable during his lifetime. Hundreds of thousands more words. Newton had become completely dogmatic about his own theories. Light was particles, not waves. He was wrong. Calculus was his alone. Leibniz had equal claim. Gravity worked exactly as he described. No modifications needed. Einstein would later refine it. Science requires questioning and revision. Theories need testing and updating. But Newton couldn't accept any challenge. His followers didn't dare question him. Progress requires building on and sometimes correcting previous work. Newton made himself an obstacle to progress. Newton believed he'd been chosen by God to reveal truth, that his insights were divine inspiration, that critics weren't just wrong, they were fighting against God's revealed truth. This messianic self-concept justified everything. The feuds, the cruelty, the vindictiveness. Even before Newton died, his followers were creating the Newton myth. The perfect rational scientist, the founder of modern physics. But they edited out the alchemy, the heresy, the feuds, the mental breakdowns, creating a sanitized false image that would persist for 200 years. Chapter 14, The Death and Secret Papers. In early 1727, Isaac Newton was 84 years old, and his body was finally failing after decades of abuse and neglect. Severe kidney stones causing constant pain. Gout in his feet made walking difficult. General weakness and frailty. He stopped attending Royal Society meetings, was mostly confined to bed, but his mind remained sharp until the very end. Newton suffered terribly from kidney stones in his final months. The pain was unbearable. He couldn't sleep, couldn't eat, could barely move, but he refused to show weakness, refused to complain. Just endured in silence, as he'd endured everything his entire life. He moved to a house in Kensington, in West London. Cleaner air than central London. His niece Catherine Barton cared for him. Few visitors were allowed, mostly alone, as he'd lived his whole life. In March 1727, Newton's condition deteriorated rapidly. He couldn't leave bed. The pain was constant. Doctors could do nothing. He knew death was approaching, and according to witnesses, he refused last rites, refused to take Anglican communion. Communion required affirming Trinitarian doctrine. Newton couldn't do it. Even dying, he wouldn't compromise his beliefs, wouldn't pretend to believe in the Trinity. 60 years of secret heresy. He stayed true to it to the very end. He died early morning, March 20th, 1727, by the old calendar. March 33rd, 1727, by the modern calendar. Age 84 years, at his house in Kensington. Catherine Barton and a few servants were present. No dramatic last words were recorded. Newton died without publicly confessing his heretical beliefs, without revealing his Arian theology. He'd kept his anti-Trinitarian views secret for 6 decades and took them to the grave, protecting his reputation to the final moment. Isaac Newton received a state funeral, the first scientist ever honoured this way, and the irony was thick considering who Newton actually was versus who people thought he was. Held at Westminster Abbey, attended by nobility, scholars, government officials, massive public turnout, the greatest scientist buried among kings, a national hero's send-off. 2 dukes, an earl, and 3 other nobles carried Newton's coffin. The greatest scientific mind in history, honoured like royalty. This would have satisfied Newton's ego enormously. The fatherless farm boy, buried like a prince. A grand monument was erected in Westminster Abbey, showing Newton reclining, surrounded by cherubs holding symbols of his discoveries. Prism, telescope, astronomical instruments. The inscription called him the glory of the human race. No mention of feuds, heresy, cruelty. Just sanitized genius. Worth over $30,000 at death. An enormous fortune for the time. Left to nephews and nieces. Catherine Barton received the largest share. No wife, no children to inherit. Wealth from his mint position and investments. Newton's heirs inherited multiple trunks filled with manuscripts. And when they opened them, they found hundreds of thousands of pages on theology, alchemy, biblical prophecy, heretical religious views. They didn't know what to do with this material. The family was horrified. These papers, if published, would destroy Newton's reputation, reveal him as a heretic, a mystic, an alchemist, contradict the rational scientist image. The family decided to suppress them, locked them away. The day Newton died, he was already being transformed into myth. The rational scientist, the founder of modern physics, the man who explained the universe. All true, but incomplete. The real Newton was far stranger, more complicated, more human. Over 1 million words on heretical theology, extensive alchemical experiments and theories, biblical prophecy interpretations, chronologies based on dubious methods, the cruelty to rivals, mental breakdowns, vindictiveness and pettiness. Almost immediately after Newton's death, his followers and the Enlightenment created a sanitized myth that bore little resemblance to the actual man. Voltaire attended Newton's funeral and wrote glowingly about English respect for genius, contrasting it with France's treatment of intellectuals. Voltaire spread the Newton myth across Europe, the perfect rational genius, the embodiment of Enlightenment reason, the scientific achievements, real, the Principia, a masterwork deserved, laws of motion and gravitation, revolutionary, mathematical genius, undeniable, rational empirical method, partly true, alchemy, not revealed for 200 plus years, heretical theology, suppressed by the family, the feuds downplayed as minor priority disputes, mental illness, not discussed publicly, cruelty to rivals, excused or ignored, vindictiveness, attributed to justified defense of truth. The 18th century Enlightenment needed heroes of reason, needed to believe human rationality could understand nature. They needed Newton to be the perfect embodiment of rational thought. So they made him that, erasing anything messy or contradictory. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Beautiful poetry, but it made Newton divine, not human. Implied his work was revelation, not labour, made him more than human. The papers were named after the Earl of Portsmouth, who inherited them. Kept secret in the family for over 150 years, not examined by scholars until the late 1800s, not fully catalogued until the 1900s. They revealed the other Newton that contradicted the myth. Science needed heroes and clear narratives. Newton's work, genuinely, was revolutionary. It was easier to celebrate genius than understand complexity. Acknowledging his flaws seemed to diminish his achievements. The myth served cultural purposes. The truth was uncomfortable. Only in the 20th century, when Newton's private papers were finally studied, did scholars discover the real Newton. The alchemist, the heretic, the mystic, the vengeful feuder. And they were shocked. The founder of rational science believed in biblical prophecy and transmutation of metals. And that's the story of Isaac Newton, the man who watched an apple fall and saw the hidden force behind everything. Look, if you genuinely enjoyed this, if this kind of content is actually valuable to you, then go ahead and like, comment where you're from, and subscribe, but only if you really mean it. Your support helps us keep making these stories.